Hello, my name is Shahriari, and this is a lecture in a series of lectures on introductory undergraduate linear algebra based on my book Retrolinear. The subject of this lecture is linear transformations. We will give the definition and we look at some examples. There is a previous video where we motivated the study of linear transformations by asking when are two vector spaces the same. In this video, we will be just remind you of the definition and doing some examples. So let's get started. So let me remind you very quickly what a vector space is. A vector space is a non-empty set together with two operations, an addition and a scalar multiplication. The whole situation is quite abstract in that I'm not telling you what the elements of the set are, and I'm not telling you what the operations are. All I'm saying is that there is a set, and you can add two elements and get another element in the set, and you can multiply by scalars every element of the set and get another element of the set, but the addition satisfies certain sort of straightforward properties, and the scalar multiplication does the same. And if you have this situation, then you have that V with these two operations is a vector space. Watch my videos on a definition of a vector space and all the examples and so on before you proceed if you have never heard of a vector space. Now, when we have two vector spaces and we have a function between them, if we want to use the function to relate the linear algebra properties of V to W, then we wanted to have certain properties regarding addition and scalar multiplication. So in particular, if the vector V1 in V is sent somewhere, maybe it's sent to T of V1, the vector V2 is sent to T of V2, we don't want V1 plus V2, we don't know where V1 plus V2 goes, but we don't want it to go willy-nilly any place it likes to. If this is going to be a map that's going to tell us about we will be able to do things with it and linear algebra, we want V1, if V1 plus V2, which is the sum of V1 plus V2, should go to the sum of T of V1 plus T of V2. So that means T of V1 plus V2, T of V1 plus V2, which is where V1 plus V2 goes, should be T of V1 plus T of V2. So so this is what a property of the function that I want. Functions in general don't have to have this property, but for these particular kinds of functions, I would like them to have the property that T of V1 plus V2 is T of V1 plus T of V2, no matter what V1 and V2 in V I pick. The upside down A is means for all. Similarly, for scalar multiplication, I want T of a scalar times V to be the same as that same scalar times T of V. Now, scalars are, in this course, for first-time viewers, they are just the real numbers. But as we have discussed in previous videos on fields, the scalars in a vector space could come from any field. And for second or third time viewers, you can replace R with any field. But for the purposes of going through this the first time, just think of real numbers as being the scalars. Okay, so now let me make that precise. So I want to tell you what a linear transformation is. This is a central core topic in linear algebra, so you want to sort of understand it well. So the ingredients are you have two vector spaces, V and W, and you have a function from V to W. So V is the domain and W is the codomain, and T takes elements of V and throws them at W. It eats elements of V and produces elements of W. Now this function doesn't have to be a linear transformation, but it is a linear transformation if it has these two properties. If T of V1 plus V2 is T of V1 plus T of V2, and T of alpha V is alpha T of V for all those concerned. We call these preserving addition, preserving scalar multiplication, or we call those the linear properties. Those are the linear properties that a map may or may not have. If they do, then the map is called the linear transformation. Now, sometimes we actually like to have linear transformations from a vector space to itself. And that means that you're taking elements of a vector space and sending to somewhere else in the vector space. And for those, we want to think of that as you're operating on the vector space. You're doing something to that vector space. And we sometimes use the vocabulary linear operator for those linear transformations. So a linear operator is a linear transformation. You could just keep saying linear transformation. But if you hear linear operator, you know that you have a linear transformation, but you have a linear transformation from a vector space to itself. Also, in a previous video, we discussed this, and in later videos, we're going to go into more detail. If you have a linear transformation that also happens to be one-to-one and onto, a linear transformation doesn't have to be one-to-one onto, but if it is, then it's called an isomorphism. And in that case, we want to think about two vector spaces that have an isomorphism between them as the same in linear algebra. But that's actually, again, the subject of other videos. So let me give you an example. So P2R is polynomials of degree no more than 2, polynomials of the degree less than or equal to 2 together with the 0 vector, and R2 is 2 tuples. And so I'm going to give you a function from P to R. The domain is P to R and the codomain is R2. And I'm going to tell you what the rule is. And the rule, to tell you what the rule is, I have to tell you what every typical element of P to R, every polynomial of degree less than or equal to 2 goes to. And a typical polynomial is something like it has a scalar alpha, it has its constant term alpha plus beta times x. That's the x term. And then there's an x squared term plus gamma times x squared. And this is where it goes to. And this is a 2 tuple. And so that's an element of R2. Where does it go? It says take the constant term and add it to the twice the coefficient of x, and then take 3 times the coefficient of x squared minus the constant term. And those are going to be your two R2s. And my question is is this a linear transformation? It is a function from P2R to R2, but does it satisfy, does it pass the test of being a linear transformation? Does it rise to the equation? So to do that, first of all, I have to check this, that if I take two polynomials, two elements of the vector space P2R, so P and Q are two elements of P2R, is T of P plus Q the same as T of P plus T of Q? So I have to check that. How do I do that? Well, first, I say, well, what is P? P is a polynomial of degree less than or equal to 2. So P looks like, I don't know exactly what, I can't do one example, so I have to do this in general. P is alpha 1 plus beta 1x plus gamma 1x squared, the typical polynomial of degree 2. Same with Q, is alpha 2 plus beta 2x plus gamma 2x squared. So now I've got to find T of P plus Q and see if it's T of P plus T of Q or not. So what is T of P plus Q? Well, it's T of P plus Q, but P was alpha 1 plus beta 1x plus gamma 1x squared. Q was alpha 2 plus beta 2x plus gamma 2x squared, and I have to add them. So it's T of those. But I don't know how to find T of such a mess like this. My rule didn't tell me that. My rule told me what I can do if I have a constant term, an x term, an x squared term. So at first I have to combine like terms, and I can do that. The constant term is alpha 1 plus alpha 2. Then I have beta 1 plus beta 2 times x, and then I have gamma 1 plus gamma 2 times x squared. And as soon as I write it like that, I know what my rule says. My rule says take the constant term and add it to twice the coefficient of x. So I take the constant term, which is alpha 1 plus alpha 2, and add it to twice beta 1 plus beta 2. And I do the same thing for the second entry, 3 times the coefficient of x squared minus the constant term, and I get this. But now I'm living in R2. Now I've moved over to R2. In R2, I know how to manipulate things. For example, I can split this up into 2 terms. All the things with subscript 1 in one place, and all the things with subscript 2 in the other. So I will get that. I get alpha 1 plus 2 beta 1 as the first entry, 3 gamma 1 minus alpha 1, plus alpha 2 plus 2 beta 2, 3 gamma 2 minus alpha 2. If you add these two, you get that sum again. But now I notice that this first term is actually T of P, and the second term is T of Q. So I proved that T of P plus Q is T of P plus T of Q. I'm not quite done. I have to prove the same thing for scalar multiplication. It's going to be similar. You could skip the next little part of the video if you like, or you can go through with me. So again, I have a map from P2R to R2 defined by T of alpha plus beta x plus gamma x squared equals alpha plus 2 beta 3 gamma minus alpha. And the question is that, does it respect scalar multiplication? So again, I have a typical polynomial, a plus bx plus cx squared, and I have a typical scalar alpha. And again, for the first-time readers, we're assuming that all the scalars are real numbers. In fact, in this particular case, I have to do that because the vector spaces are defined over real numbers. If this is the scalars for this polynomials like degree less than or equal to 2 is real numbers, and for R2 it certainly is real numbers, and therefore I have to pick my alpha to be in real numbers. I don't have a choice. But if I had a different example for a different vector space, then I might have changed the scalars. So, and the question is that, is T of alpha P the same as alpha times T of P? And again, the proof of the pudding is in the eating. I have to see if it is or not. So I'll start with T of alpha P and see what it is. Well, what's alpha P? Alpha P is alpha times P. Alpha times P, I can multiply. It's alpha A plus alpha beta Bx plus alpha Cx squared. And when I have it in this form, I know what T does to it. It takes the constant term plus twice the coefficient of x, and then takes 3 times the coefficient of x squared minus the constant term. So it gives me the following thing. But I can factor an alpha out because, again, I am in R2, and I get alpha times a plus 2b over 3c, alpha plus 2b, 3c minus a, and that is T of P. That's what T of P is going to be. And so I have alpha times T of P, and I've proved that I have both properties, and so I've proved to you that this T is a linear transformation. T is not one-to-one. For example, if you take T of x squared, that means that alpha and beta are 0 and gamma is 1. You get 0, 3. But you get the same thing if you put T of minus 3 plus 3 halves x. If you, instead of a, you put you put minus 3, and instead of beta, you put 3 halves, and you put gamma equals 0, then you get 0, 3 again. So this map is not one-to-one. So this is not an isomorphism, for example, but it is a linear transformation. Okay, so let's look at another example. Let's look at a map from R2 to R2 given by T of alpha beta equals alpha beta squared. This is a function from R2 to R2. The question is it a linear transformation? And this square should give you the warning sign that it's not going to be linear. But how do you prove that? You don't go through the motions of proof. You could start and see where things go wrong, but to convince me that this is not a linear transformation, which it's not, all I have to do is to give you an example. So this is what I'm going to do. So is T a linear transformation? I'm going to say, well, if I look at 0, 1, see where it goes, and then I look at twice it, is T of twice 0, 1 the same as twice T of 0, 1? That's one of the things that has to be true. It's a very particular thing that has to be true, but it has to be true nevertheless. If it's not true, then I've proved to you that this is not a linear transformation, because to be a linear transformation, those properties have to be true for all vectors and all scalars. As long as they fail once, they fail altogether. So T of 2, 0, 1 means T of 0, 2. And T of 0, 2, beta is 2 here and alpha is 0, is going to be 0, 4. On the other hand, 2 of T of 0, 1 is twice 0, 1, because if you plug in 0, 1 here, you get 0, 1, and so you get twice that, and you get 0, 2. And then that says that they are not equal. 0, 4 is not the same as 0, 2, and so T is not a linear transformation. So again, to prove something is a linear transformation, you have to show that it preserves addition, it respects addition, and it respects scalar multiplication. But to show that's not a linear transformation, you just have to give one particular example. Now, I want to show you that linear transformations come up often. In fact, you have been working with linear transformations all along, for example, when you were doing calculus. So take the function d from polynomials of degree less than or equal to 3 to polynomials of the degree less than or equal to 2. When I say that, I include the 0 vector in both of them, the 0 polynomial. And this is a map that goes from 1 to you feed it a polynomial of less than or equal to 3, degree less than or equal to 3, and you get out a polynomial of degree less than or equal to 2. But what is the rule for doing that? It's taking derivatives. So you take the derivative of the polynomial, and that's what happens. This is the derivative operator. Now, I claim that this is a linear transformation. Not only that, those things we need to prove are things that you've already seen. As an example of what this is d of, here's a polynomial of degree 3, 3x cubed minus 2x squared plus 5x minus 7, and its derivative is 9x squared minus 4x plus 5, and that's a polynomial of degree 2. So this function takes a polynomial and gives me another one of lower degree. Now, this is a linear transformation because if I take d of one polynomial plus another, that means that I've got to take the derivative of the sum, px plus qx, and take its derivative. But the derivative of a sum, when you want to do that, you take the derivative of the first one plus the derivative of the second. That's one of the things that you have learned in calculus, that when you have a sum of things and you need to take the derivative of them, you take the derivative of this one plus the derivative of that plus the derivative of that. That's actually what makes taking derivatives a little bit easier. And p prime of x is the d of p of x, and q prime of x is d of qx. So I just showed that d respects addition. What about scalar multiplication? Well, what's the derivative of alpha px? Well, it's the derivative of alpha px. But when you have a constant times something, the constant comes right out. You get alpha times the derivative of the rest. And this is exactly alpha times d of px. So the derivatives are a linear transformation. And not only that, but the fact that they're a linear transformation are things we've been using all along. The fact that when you take the derivative of something times a constant, the constant just comes out and you take the constant times the derivative. And also when you are adding two things and want to take the derivative, you just take the derivative of one plus the other. Now, here's another one about integration. Now, the setup is a little bit more complicated. V here itself is made up of functions. So V is a vector space of functions. What kind of functions? Functions that their domain is 0, 1. So the kinds of things I plug into these functions are numbers between 0 and 1. And what I get is a real number. Real valued functions on the interval 0, 1, but not all functions, but the continuous ones, functions that are continuous. So one element of this vector space might be e to the x. I can plug in anything between 0 and 1, and I will get a real number. It could be sine of x. It could be cosine of x. It could be x squared minus 2x. Those functions, the continuous functions that you can plug in anything between 0 and 1 and you get a real number, form a vector space. You can add them. Like, for example, you can take x squared plus 2 and add it to e to the x, and you get x squared plus 2 plus e to the x. You can multiply them by a scalar. You can scalars. You can take sine of x and multiply it by 5, and you get 5 sine of x, and the scalars are real numbers here also. So this is my vector space V. Functions, continuous functions from 0, 1 to r. And W is also functions, but this time I'm a little bit more stringent, and I want differentiable functions, functions that have a derivative, and also whose domain is 0, 1, and codomain is the real numbers. Now, go back to my videos on functions to note that I decide what the domain is. Don't tell me that e to the x's domain is all real numbers. Well, that's the largest domain you could have for it, but I can decide that I'm going to only focus on e to the x when I plug in numbers between 0 and 1 and get real numbers, and that therefore e to the x is both in V and in W because it's both continuous and differentiable. So V and W themselves are made of functions, but now I'm going to give you a function that goes from one to the other. So I'm going to define a map from V to W. So note that T, the function, is going to eat functions. You're going to feed it a function and comes out another function. Hopefully, if I haven't made a mistake in telling you what the function is. And the functions you feed in are continuous, but the functions that come out are nicer. They're differentiable. They're smooth. And it's defined by the integral from 0 to x of f of t dt. So this is an integration operator. So first thing is to ask is t of f actually a function? So f is a continuous function, is in V, so it's a continuous function from 0, 1 to r. When I feed it, do I get a function of x? Is this actually a function? And the answer it is. It looks like an integral, but it's not a number because this upper bound is x. So if this was an actual function and you took the antiderivative, then you would plug in x and you would apply 0, all the t's would go away, and you would be left with some jumble of x's, and that would be a function of x. T is called a dummy variable. This is not a function of t, it's a function of x. And this is a way to define functions using integrals. Now, not only that, so for example, t of e to the 3x, y equals e to the 3x is a function. So if you want to use this, you plug in e to the 3t here and integrate it from 0 to x, and you get, what you get is 1/3 e to the 3x minus 1/3, and you get a different function. Now, do I get a function in W? I get a function, but do I get a function in W? And the answer is yes, because these functions, by the fundamental theorem of calculus, the functions that I got by integrating are going to be differentiable, because the derivative of t of f, the derivative of this is just going to be f of x actually. And so, actually, I'm getting a function whose derivative is the function that I fit to the original to my operator. So again, this is a function that eats functions and outputs functions. And so the question is it a linear transformation? And it is. So why is it a linear transformation? Because again, the properties I need to prove that it's a linear transformation are things that you've been using all along. This is why linear transformations are important. They actually come up all over the place. And in fact, you have been using these properties. You just haven't been naming them. Now we have a name for them. You can impress your friends by the fact that you know this. But also we're thinking of these properties that integration has, differentiation has, and other things have as sort of a common property, something that they share. We are making connections between them. So why this is a linear transformation? Because if I find t of f plus g, what does that mean? That means that I have to find the integral of f plus g from 0 to x. But that's the same as finding the integral of f of t plus g of t from 0 to x. And when you are integrating a sum, you can split it into two integrals. That's, again, something that you've been doing in calculus all along. So you have to do the integral from 0 to x of f of t dt and the integrals from 0 to x of g of t dt. But those are t of f and t of g. So I proved to you that t of f plus g is t of f plus t of g, and t respects addition. What about multiplying by scalar? Well, what's the t of alpha v? That would be the integral from 0 to x of alpha f of t. But that's the same as alpha of f of t, and you have to integrate that. And in an integration, whenever you have a constant multiplied, you can bring that outside. And again, that's a property that we've been using all along. And so we have alpha of the integral from 0 to x of f of t dt, and that's alpha t of f also. So t is a linear transformation. And again, those linearity properties are things that you're familiar with. So here's another example, and this is a slightly different example because of the fact that it works for any vector space. So start with any vector space and pick any scalar that you like. And again, the scalars could be real numbers, or depending on what your vector space is, what the scalars in that vector space are, and they don't have to be real numbers. So define t from v to v, and the definition is this, that you take any vector and just multiply it by lambda. So you're taking the vectors, this is a linear operator. It's going to take any vector in v, and what you're going to do is multiply by scalar and get something else in that vector space. Now, this is a linear transformation. I can prove it in general, regardless of what the vector space is and what the scalar is, because what's t of alpha v? Well, t of alpha v, I'm going to do scalar multiplication first. It's going to be, well, you have to multiply this by lambda. This is what you do with any vector. You multiply it by lambda. But lambda and alpha are both scalars, and it doesn't matter which order you multiply them. This is the same as alpha times lambda v, and that's the same as alpha t of v. What about addition? What's t of v1 plus v2? What do we do with any vector? We multiply it by lambda. T of v is lambda v. T of apple is lambda times apple. T of Fred is lambda times Fred. And T of v1 plus v2 is lambda times v1 plus v2. But lambda times v1 plus v2 is the same as lambda v1 plus lambda v2. That's one of the properties of a vector space. And lambda v1 is t of v1, and lambda v2 is t of v2. And so I've proved to you that this is a linear transformation. Now, special cases of this actually sometimes are given some different names. So for example, if lambda is 0, then t of v will be 0 for everything. This is not a very exciting linear transformation, but it actually ends up being an important one. It's the linear transformation that takes everything and sends it to 0. So funnels everything to 0. And not surprisingly, this is called the zero linear transformation. But this is an example of this multiplying by a scalar. If lambda is 1, still not very interesting. This is actually maybe even less interesting. It sends every vector to itself. And this is called the identity linear transformation. Now, there's other ones that have other names that people sometimes use. I tend not to use those that often, at least in this set of lectures, but you might want to be familiar with them. If lambda is between 0 and 1, then t is called a contraction. So that means like for example, lambda could be 1/2. That would mean that every vector is sent to 1/2 itself. It's just everything shrinks by 1/2. So that's called a contraction. And if lambda is greater than 1, then sometimes it's called a dilation. Okay, our final set of examples are something called matrix transformation. And these tend to be the most important set of linear transformations. In fact, this will tell us how to make linear transformations at will. So and I'm going to write this as a lemma for that reason. So let's say that you start with an m by n matrix with real entries. So and again, if you were interested in linear transformations from other types of vector spaces, you might start with entries other than reals. But m by n, m rows and n columns. So you're sitting there, a matrix walks through the door. Well, what this lemma tells you is that as soon as this matrix walks through the door, you really have a linear transformation. What is that linear transformation? Well, define a function that I'm going to call LA, L sub A, and I'm putting that A there because this map is defined using the matrix A. Define a map LA that goes from Rn to Rm. A was m by n, m rows, n columns. LA goes from Rn, then n is the number of columns, to Rm, where m is the number of rows. And how is the map defined? Well, if you take any vector in Rn, you multiply it by a. You say a times x. So LA of x, LAX, is a times x. A was m by n, x is n by 1, and so when you multiply them, you get n by 1. So you go from you get it, you're feeding it something in Rn, and you're getting something in Rm. And the lemma, the content of this lemma, is that this is a linear transformation. And this is important because if your day job is to find linear transformation, and your boss comes to you every day in the morning and say, give me a linear transformation from this Rn to that Rm, you can say, yeah, that'll take me a little bit of time, but I'll do that. But then you can do it very quickly by just writing down a matrix. If this is correct, which it is, then you can create a linear transformation from just any kind of a matrix that we write down. And you can then spend your day checking your notifications instead of working. So let's see, why is this a linear transformation? So before I prove that, let me just give you an example just to make sure that we understand perfectly well how you make a linear transformation out of the matrix. So today, this matrix walked through the door. This is a 3x2 matrix, 3 rows, 2 columns. The first column is 3, 0, 1. The second column is -2, -1, 2. And how do I make a linear transformation out of it? First of all, the linear transformation goes from where to where? The linear transformation goes from R2 to R3 because there are 2 columns, 3 rows. And it's defined by where does a typical element of R2 alpha beta go? Well, it goes to A times alpha beta. And in this case, you could actually multiply the matrix by alpha beta and see what you get. So, and you get LA of alpha beta is 3 alpha minus 2 beta minus beta alpha plus 2 beta. So this is a function. You could now erase the matrix and just pay attention to this is the definition of the function. And what we're saying in the lemma is that if you make a function like this, you don't have to go through the motions of figuring out if it's a linear transformation or not, because once for all, in the proof of the lemma, we're going to prove that all these kinds of functions are linear transformations. So this is what I want to show, that you have got an n by n matrix. I want to show now that it is LA is a linear transformation. So how am I going to prove that? So I pick 2 elements in Rn and a scalar, and I've got to show you that the linear transformation respects the addition, and it also respects the scalar multiplication. So what about LA of x plus y? Well, what is that? How do you find LA of x? LA of x is A times x. What's LA of apple? It's A times apple. What's LA of Fred? It's A times Fred. So what's LA of x plus y is x times x plus y. But this matrix multiplication can be distributed, so we get ax plus ay. But ax is LA of x, ay is LA of y. So I prove to you that the property that I want, that LA of x plus y is LA of x plus LA of y. And the scalar multiplication is the same. What's LA of alpha x? Well, again, LA of Javad is A times Javad. So LA of alpha x is A times alpha x. But that alpha is just a scalar. It doesn't matter where it is. It can come out. And so this is alpha times AX. And AX was LA of x. So alpha, I get alpha of LAX. So I prove to you that these things that I would get from matrices are always a linear transformation. This is an important thing because this is sort of a gestalt point. It's a point where our lens can change, our point of view, our paradigm can change. So if a matrix walks through the door, if you're an untrained eye, then you think of it as an array of numbers. A matrix came in, so it's just a bunch of numbers that someone is giving to me. And that can be useful. A lot of times in data, if you have data, you might arrange it in a table, for example. A more sophisticated version is to say that, a matrix walked through the door, there's 3 vector space subspaces that are important: the column space, the row space, and the null space. And these are all going to give me information. In fact, in this series of lectures, we've been exploring what information can be gleaned from the column space, row space, and null space. We have found some of it, and in fact, more is in after our new point of view about thinking of matrices about linear transformations, we will actually gain even more insight into these subspaces. But looking at these subspaces, I have a column space, that's the space spanned by the columns. I have a row space, the space spanned by the rows, and I have a null space, the solutions to x equals 0, and those tell me something about the matrix. That's a more sophisticated way of thinking about that matrix that just walked through the door. Watch my videos on those things if you don't know what I'm talking about. But now we have a new way of thinking about it, which is that we can think of this matrix as a function, and not just any function, but a linear transformation. And this gives us a different set of imagery. So when you think of a function, a linear transformation, you can ask questions like, is it one-to-one? Is it onto? As a function, does it have an inverse? Now, as a matrix, we have been asking that question. does the matrix have an inverse? And the question would be that if you think of a function and are those things related or not? Spoiler alert, they are. But the point is that when you think about array of numbers, there's certain things you think about. So numbers, you can do things with them. If you think about vector spaces like column space, row space, and so on, you have a different set of questions, different set of vocabulary, different imagery that you have associated with them. What's a basis? What's a dimension, and so forth. And when you have a function, you have yet another way of thinking about this object, this matrix. And this switching from one point of view to another tends to be really important. You don't want to be stuck in one point of view. You want to just go back and forth from this and that. And the same thing is true again for matrices over any field where the entries are not in real numbers for any field. For those, we don't get linear transformations from Rm to Rn, but we get them from Fm to Fn, and those are vector spaces over the field F. Now, the fact that matrix transformations are linear transformations can be a sort of a shorthand way for finding if something is a linear transformation. So let's say that someone gave you a function, this function from R2 to R2, and you wanted to know, is this a linear transformation or not? The way we started the lecture, and through a number of examples, what we did was, well, okay, let's show if it respects addition, if it respects scalar multiplication, but those calculations can be somewhat tedious. Now we have another way around it. So what we can say is that, so to answer the question, is T a linear transformation? I can say, well, look at this matrix. Now, this matrix didn't come from nowhere. I looked at my my linear transformation and somehow concocted this. And in fact, later on, we'll do this systematically and figure out how to go from a linear transformation to a matrix and how to find the matrix of a linear transformation. But I'll say, look at this matrix, and then look at the matrix transformation that I get from that. Any matrix gives me a linear transformation. What is it? Well, it's a map from R2 to R2, and it's defined by what? What's LA of alpha B? Well, like any linear transformation coming from a matrix, it's A times alpha B. But A is this particular matrix, and if you multiply this, you will get 4 alpha plus 7 beta, and then 7 alpha minus 4 beta. So this is actually the matrix transformation that I get from this matrix is that original the map that you gave. So LA is actually T. So among other things, now I know that, so LA of alpha beta is the same as T of alpha beta. So I know that T is the same as LA. And so now I know that T is a linear transformation since LA is. So this is a proof that T is a linear transformation without getting my hands dirty and looking at T of x plus y and T of alpha x. But instead, just pointing out that if you look at this matrix, then T is really in disguise a matrix transformation, a linear transformation that was constructed from a matrix, and because of that is a linear transformation. Now, this is, as I said, a lecture in a sequence of lectures on linear transformations. This was the second one, but there's going to be another one on basic properties, then on image, the kernel, more on matrix transformations, the rank nullity theorem, a very important theorem, and then we go back to isomorphisms and try to discern for how many vector spaces of different kinds are there to begin with. So this is the end of this lecture. Please subscribe if you want to be subjected to more math videos, and like this video if you liked it. And I will see you at the next lecture.